There we go. So now I'm recording, and this is the last lecture of this digital signal processing topic. It's about embedded systems and the special uh, things that you need to take care when you are dealing with the embedded systems. Embedded system usually means, I'll say, limited computing power, and that actually brings us some opportunities to make shortcuts. So actually this is not too the long session. I think we will be done in less than 1 hour, so we can then decide if we want to continue directly to the exercises or have a break. But anyways, so embedded systems, it's all about performance. So basically the digital filtering requires fast arithmetic operations, namely multiply, accumulate operations. There's an example of finite impulse response system calculation when you just can use this difference equation since you don't have the feedback unless you want to. And basically you just calculate the value of the output based on the input and the weighted input, and the weighting parameters are the impulse response values. On a code, it could look like that. Actually, this is one of my what I have done in my own examples on the classes when we have some hardware, very simple calculations, and then basically, okay, that's the easiest way to calculate if you take into account some say special things like what kind of numbers you have. So if you have integer numbers, you need to make sure that the integer numbers which are holding the data have long enough the word length that you can actually, for example, multiply to 8-bit signed values. That takes 16 bits to save the whole value. Or you can actually just multiply and cut the remaining, since that's just decimals. Well, okay, not quite, but anyways. And then you need to also make sure that you are not getting overload. What is that? Arithmetic overflow due to the that you are summing values and you're overflowing that way. So those couple of considerations, but otherwise that's just works. Or if you are dealing with the floating point values, then this is straightforward. Okay, but anyways, the performance comes from the fact that you have a multiply operation, okay, pointer. So multiply operations, and you have a summation operation, so accumulate operation. This is actually accumulate. So, so that's the what takes the time. And when you have the embedded processor, the how this multiply accumulate can be done or should be done depends highly on the processor architecture. If you have floating point system, a processor with a floating point arithmetic unit on it, then everything is easy. You just use a MATLAB, you do to design the filter, then just take those values and this filter coefficients and just save those in H file and then just include that one into your code. It's really easy. but in general, there is a cost on floating point versus fixed point. Okay, that's a little bit too big statement here. Fixed point gives better performance. No, it doesn't. If you have a highly tuned floating point arithmetic unit, then it actually does these calculations at least the same speed as fixed point. But it takes about double the silicon space. So floating point ALU actually takes about double the silicon space, meaning that it increases the price of the processor. So basically, in that sense, fixed points give better performance for the same price the chip. Okay, if you have any modern embedded processor, they usually have a separate MAC unit, so multiply accumulate unit. It's basically it's not that much silicon as making the full the floating point unit there, but it's a specialized addition next to the arithmetic logic unit, which is designed to do nothing more than multiply, accumulate operations. Any processors which has basically when the manufacturer mentions about DSP, what is that called? DSP, the DSP something support. Yes, DSP support. It usually means a separate MAC unit to do these calculations, but this is like IKEA furniture. Some assembly may be required. Yeah. So what I have encountered is that although these processors come with the MAC unit, they usually the compiler doesn't know anything about it, not yet. There's of course there are some exceptions on that one. Okay, and then there's what is the another possibility? Well, you can always use software floating point arithmetic. Even 8-bit processors usually, well, any processor can which has ALU can do floating point calculations with the software. And basically, if you get a full license of microcontroller, this compiling environment, basically they come also with the floating point support. I have the last time I have been using that was on the Hitachi 8-bit core and Keel compiler had actually single precision floating point, but then a single multiply accumulate operation would take thousands of instruction cycles instead of just few cycles on the native 8-bit word length. So basically, you can do it, can do floating point arithmetic in any processor environment. It just may take way too long time. But okay, still, if you have processing power enough and you are not worrying about, for example, battery lifetime, thinking of a system that makes a lot of those Mac operations, it might actually mean that you cannot put that processor core to sleep at all since it's doing these floating point operations. So in that sense, you need to think of, is it smarter to make fixed point system? Then there's that which is called fused multiply add acceleration, which has basically, well, it usually means a floating point Mac instead of the full floating point ALU. But again, it's some specialty. Sometimes 16-bit processors actually I have seen using fused multiply add acceleration. But on 32-bit processors, it's either full floating point Mac or the full floating point ALU or just these with this normal ALU. Okay, then there's a separate family of specialized processors called digital signal processors, which actually use, for example, parallel processing, pipelining, that kind of stuff to do those Mac operations as fast as possible. So when we are talking about digital signal processor, that's a highly specialized processors to do Mac operations. It's nothing more than that. And then we have there the floating point systems and we have fixed point systems. The fixed point digital signal processors usually are giving you better performance for the money. But if the money is not if you have enough money to spend, then floating point digital signal processors actually they give you a at least simpler way to do things, and sometimes it gives you the only way to do this, do some of these applications. But anyways, there's a lot of choice from 8-bit processor where you must do software up to the digital signal processors where you actually do there are these Mac operations on single cycle and pipelining, and wow, they are just screaming when they're crunching the numbers. One place those digital signal processors are used is on the graphic processors, graphic cards. So if you are playing, for example, some computer game that requires the changing of those triangles, there it requires a lot of computing power and especially the Mac operations. So these graphic acceleration cards are one sort of special digital signal processor cards. Okay. Then let's see. I assume that you know something about fixed point presentation of numbers. The fixed point is practically you do these arithmetic operations in integer instead of floating point, meaning that you have fixed point and let's see, the beginning of this word, data word gives the numbers, the integer numbers, and then the rest of that is defining the fractions. So in one sense, you can think of the decimal point is fixed in a location by dividing the original integer number by some 2 to the power of something, which means that multiplication, you do integer multiplication and then fix this decimal point. Very simple operation, especially for the fixed point digital signal processors, where this fixed point presentation is a native data presentation. And then multiplication of two fixed point numbers, you first set this decimal point at the same align these do two words so that your decimal points are on the same place, and then you just use integer ALU to add the numbers. So it's quite practical way of thinking into rethinking integer numbers. Okay, so quantization for parameters. Quantization basically means that the floating point accuracy cannot be used, and then we need to go into fixed point, which means a fixed word length. And oh, sorry, there's some data is missing there, and some words are missing. I try to fix that one. Just making a note of that. That's actually an example what happens to a filter. That's infinite impulse response filter, elliptic, I would guess, since it has a quite flat response on also on the stop band. Floating point arithmetic is the blue line, and then I start rounding the floating point number, the filter coefficients, and this is actually direct form filter. So if I round these floating point coefficients in the 16-bit presentation, only 16 bits, basically I start having something funny going on the passband. Okay, the stop band is usually not that bad for IIR systems because the amplitude response of the IIR system is dominated by the poles which are close to the unit circle. So even if the zeros are moving a bit, it usually does not affect so much on the stop band attenuation, but the passband ripple and passband behavior of the filter are usually affected a lot. Here's the 16-bit, and then at 8 bits, this is not the same filter anymore. The cutoff frequency has changed. Well, it's already changed here, but that's quite, sometimes this is tolerable. Let's put it this way. But this is totally different filter already. It has attenuation on the passband also, and this cutoff frequency has changed from 400 hertz to about 220 hertz or so. Okay, so unusable filter at 8-bit resolution. Okay. Just a reminder, we have different ways of representing the system or breaking it up. So we can actually have cascaded systems. And earlier we have calculated this on the second exercise. There was the systems where you calculated what is the transfer function of the combined system if you combine them in cascade or parallel. On practical filters, you are doing the actually not combining the systems so much, but breaking them up. Since the calculation errors can be minimized by dividing the nth order system into cascaded second order systems. Basically, I will show you an example why it's that. But anyways, if we take the zeros and poles and start pairing them, then any higher order system can be presented as second order system, the cascaded second order system. Maybe I should actually now use the annotation tool to show you what I'm talking about here. So if we have a zero pole plot, okay, and that's okay, it's almost there. Yeah, zeros and poles, and I'll just come a couple of zeros and poles here. So zeros are usually on unit circle, for example, here, here, and complex conjugate pairs, that one, and maybe then I would have a poles somewhere on the passband here, pairs of zeros and pairs of poles, like that. And well, I can actually take, for example, these zero, whoops, not that one. How to mark these? Okay, those two zeros and those two poles, combine those as the first system. Then I take the remaining zeros and poles, for example, these zeros and well, those two poles, and combine that into the second system. Okay, I have broken up the system into second order systems. Good. So what is so good about it? I need to draw write some text here, maybe with a nice purple. Think of the something that you learned from high school. Kind of, oopsie daisy. If you take this multiplication of z plus 1, so exponentials of z plus 1. It goes something like that. You probably remember this kind of from high school. And then somewhere in here you have da 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 in order of 100. Not the number 100, but in order of 100 here at the middle. And think of now the y of n, how to calculate y of n equals x of n. I just leave the okay, x of n plus even that fourth row here plus 4 times x of n minus 1, x of n minus 1, and so on. Okay, that will be the difference equation on that one. Think of the same thing for that line. Oops. That last line here. This is a little bit messy now. And 8-bit representation. So if this was calculated directly from direct form, meaning calculated directly from this one, basically what would happen is that you will have multipliers of 1 and 100 on the same, the weighted sum, and 8-bit presentation. It works if you have integer numbers, but if you are rounding these numbers, the corner values would have a really big, huge relative error compared to the center values, especially down here. Down here, you would have, say, these fractional errors on the center value would be very much smaller than on the corner values. So calculating the direct form response for the system would sum up these calculation errors, and that's actually what happened in this example. Direct form will start summing up the errors compared to this second order system representation or implementation. So here we have, well, about the same order of magnitude fractional errors in all filter coefficients if we break those in second order systems. So on FIR systems, what this one would do is, well, in FIR systems, you are moving the zeros. If you are doing this rounding, and that'll actually then affect on the stop band attenuation. It will make the stop band attenuation worse, less attenuation. On the IIR systems, the situation is actually even more dangerous, since you can easily move the by rounding errors, you can actually start moving the poles outside of the unit circle, which means the system comes unstable, meaning unusable. So especially in case of IIR, you want to organize the system as the second order system. Otherwise, you may end up having really bad results due to the poles moving outside of the unit circle. There. Here's an example of the SOS when you have an FIR filter. blue line, which doesn't show up because it's actually behind the red line. That's the original floating point, double precision floating point filter coefficients, magnitude response. That green actually is when you have the direct form system and 8 bits of data. So 8-bit quantization of these filter coefficients. And that actually gives you the stop band attenuation starts get less. Well, okay, 8 bits, the 8 bits singleton quantization noise level is somewhere around minus 40 dB actually. So in practice, this FIR filters, if you need to have the lots of stop band attenuation and want to use the direct form, then you basically need to have enough of bits to store that store those the store the filter coefficients. Okay, have enough of bits. But if you break that one into the second order system, in this case, actually, we can see that this 8 bits second order system representation implementation have roughly, well, that I would say exactly the same amplitude response as the original floating point design. So that's the difference. For FIRs, you are just you're just actually losing some of the stop band attenuation, which is not that dangerous if you can live with that one. Okay, it's fine. This is so-called in engineering. You do use approximations, and for some applications, this could be even more than you want, or more than what you need, even that 8-bit direct form. Since it's actually also faster to calculate, you don't have this overhead due to the function calls to different SOS routines. Okay. Here's a example of what it does for the IIR system. Okay, I have sixth order elliptic filter, floating point is a blue line, red line is the SOS system, and then the green one is the 8 bits with direct form. And as we can see, the red one using the SOS second order systems, it's much closer to the original than this 8 bits without the second order system. So that's the direct form system. Okay, so that's the difference. FIR, the stop band is affected. IIR, the passband is affected by these rounding errors. And guess what? That was all about the theory. So theory, embedded systems, everything is about performance. When you are doing digital signal processing, it means the we are mostly doing multiply accumulate operations. Processors are different. Some of them have support for DSP, some of them don't. 8-bit processors, of course, they are very cheap, but on the other hand, there are no floating point at all. The only way to do the calculations is fixed point, and then you need to, on those, usually also take into take care of those different integer numbers by yourself. Where is the point? A decimal point. Quantization of parameters. Okay, small limited systems cannot do fast calculations when you do the quantization of those floating point coefficients. Actually, you end up deteriorating the filter performance. No good. The result of the solution for that problem is using second order systems. In FIR, actually for the FIR, you usually just have a long enough word length and just use this fixed point. Since usually you think of the 16-bit numbers, you then already have enough bits for more than 80 decibels on stop and attenuation. So FIR, you could actually, if it's not, really necessary, then you could actually go with the this ordinary ordinary direct form filter. On the other hand, okay, if you have a parallel processor architecture, then you can actually pipeline these different stages. So for speed purpose, it might be even wise to break the FIR into second order systems. Okay. Okay, and then we have the IIR, where we have say more serious things happening. So basically, we can have easily a system to go unstable. Here, it's not yet unstable, but that's the second order system implementation is much better than the direct form, for sure. This is sixth order filter. It's not a high order number yet, and you already start seeing some bad results when you have say limited resolution to do the calculations. Okay. Let's have a short break now, say 10 minutes, and I will continue with this exercise. Then I need to brew some coffee. Okay, any questions? If not, then continues at there'll be 11 and 20.